Today we're going to discuss the Euclid satellite, which is
You
put
look
up
like
by
a
the
big
European.
satellite.
It is a satellite. No, the Euclid satellite is up there, but it hasn't really done much yet. It was launched by the European Union, which also hasn't done much yet. Okay. Now, here's my excuses. I want everybody to know my excuses here. This is Dr. Binnendijk. He was my astronomy professor at Penn. And I took stellar in the fall of 71, and I took solar in the spring of 71. At that time, stellar was almost all light physics. The accelerating expansion of the universe is 1997. So I'm really out of date. And it was discovered in the supernova cosmology project by Perlmutter, and then in the high super Z supernova research team. And what they found was that the distant type 1, which we'll go over all this stuff, the terminology, type 1a supernovae were fainter than expected, indicating the universe has accelerating expansion. And that led to the hypothesis. It's important to remember the hypothesis of dark energy, mysterious force driving the acceleration of the universe. But it's just a hypothesis. Now, the Euclid Space Telescope is going to map the universe to a great extent, and of course, the dark universe along with it. It's going to map more than a third of the extragalactic sky. Now, there's some parts it could map the whole thing, except that it can't see it. Behind us, or on top of us, is the Milky Way, and of course, it can't see through the Milky Way. And on the ecliptic, it can't see through the dust of the ecliptic. Those two things are simply eliminated from the map. The large-scale structure of the universe, Scott Kenyon and Margaret Geller, they talked to us about, because Margaret described the cosmic web in a very small segment of the universe. Now they're going to look at 1/3 of the galactic sky and look at galaxy distribution shapes and infer the presence and influence of dark matter. And we're going to go over redshift measurements, constant, are they constant, are they variable, are they intermittent, the redshifts, and what the role of dark energy is in all this. But first I thought we would go over some of the hardware. And this is, let me see if this works. Yeah, oops, maybe you guys want to check that. Here's the hardware. Now, this doesn't have the cover. Over here is the main mirror here. And this is not a physical column. This is just the reflection goes up to the secondary mirror here, and then down into the computing area down below here. So if we look at it again, here's the skeleton. Here's the main mirror, secondary mirror, and then down into the computing area down here. And here's just with the shell over that. So down in the guts of the machine is of course a wide-angle telescope with 600 megapixel camera for visible light, gives us brightness, the visible range, and images. And the brightness that's important in distance measurements and infrared and redshift. And then the near-infrared spectrometer and photometer will obviously look at spectrum and in the infrared and near-infrared. We can't see near-infrared. Spectrometer, this is a distinction. Spectrometer measures a wide range of wavelengths. So you're looking at redshift, you got to know what shift you're looking at, which gives you brightness. And here's what you get. So here's what you get for 1.4 billion euros. The craft is 7 meters tall and 3.7 meters in diameter. This telescope mirror is 1.2 meters in diameter. The field of view is about a degree, almost a degree. Now the main mirror, M1, is maintained at a remarkably low temperature of 130 degrees Kelvin, with thermal stability better than 50 millikelvin. So it's not going to be flexing at all, expanding and contracting. And the mirror, the construction is really made of silicon carbide, which is a good thermal elasticity at those temperatures, stiffness, and radiation resistant. And again, we have the camera, the visible wavelength, and the near-infrared spectrometer photometer. So you can see how the light's going here, bounces to here, bounces down to here. Is my cursor showing?
Yeah.
Over near-infrared, and another mirror here to the visible range. So the visible range camera is going to be used to take literally pictures of the galaxies to look at their morphology, to look at the images, the size and their shape in galaxy clustering, size and shape being influenced by other galaxies and by dark matter. So that's how they map the dark matter. And then the wavelength, which we'll go over in some detail, is redshift, and look at cosmic shear. And cosmic shear is really gravitational effect. Lensing to assess the galaxy and baryonic and dark matter. Baryonic particles are neutrons, protons, matter that we think of as matter is baryons. And the influence of large-scale structures, galaxy clusters, and dark matter on the shape of the galaxies. And the cosmic shear, just show you here the distant, we've had talks on this, the images of distant galaxies are distorted by weak gravitational lensing of large-scale structures. Here's a large-scale structure, here's a distant galaxy. These photons here are going straight out here, but they're bent and they're seen by Earth. And again, this one is bent here and seen by Earth. And then the images are formed along the gravitational lines. The galaxy shape and correlations indicate the property and evolution of large structures and geometry of the universe. And the presence of, in fact, the dark matter, of course, will be assessed using cosmic shear, because there'll be nothing there, but the light waves will be bending. And this is the view of all where that's going. Here's your visible spectrum, and here's your near infrared spectrometer and photometer. So the photometer gives a low precision redshift, and the spectrometer gives high precision redshift, and we're going to look at baryonic acoustic oscillations. So here's a picture again of the Euclid. Here's their photovoltaic cells to get energy. And they may have the sun in the wrong position, but it's pointing away into the galaxy where it can see. It can't look into the solar system. Ecliptic, which would be more on this line here. Now, it was launched by SpaceX, the Falcon 9, in July of 2023, a year ago. And it was launched by a fellow alumnus from Penn, Elon Musk. And he got his BA in the college, that's where I went. And then he got his Bachelor of Science in Economics over at the Wharton School, which is where I used to study at night. And it's positioned at the Lagrange 2, which we've all had an introduction to, is Giuseppe Luigi Lagrangia, but he made it French. And so it took a while to get there. So it's about a million miles out, the Lagrange 2. And so here's what's in some of the things that are in Lagrange 2. The Planck satellite, the Wilkinson microwave anisotropy probe, the WIND, which is waves of ionosphere and plasmasphere explorer, Herschel Space Observatory, Chang'e 2, that's from China, Gaia Space Observatory, spectrology, that's looking at, I think, cosmic rays from Russia, the James Webb, and of course, the Euclid. And of course, it's near to Earth and minimizes the fuel burn to maintain position. It's a famous astronomer here. Now, I just want to have this is obviously not to scale. I just wanted to make a point about Lagrange. If an object is rotating around the Earth here, this is rotating here, this one would have to travel faster to maintain its position. And this would fall behind. But the Earth's gravity adds to this pull. So that permits it to fly a little bit faster, so it can keep up with the Earth to a great extent. Now this I actually did study, Hubble's law of cosmic expansion. And it's called the Hubble-Lemaitre law. Lemaitre was an abbot in France. And they found the galaxies are moving away from Earth at speeds proportional to their distance. Farther away, the faster they're moving away from Earth. Therefore, the farther the galaxy, the greater the redshift. Okay, we got it. Now, I always like a little academic skullduggery, so I always look for this stuff. Hubble published his article in 1929 in the Proceedings of the National Academy of Sciences, a well-read journal. Everybody reads that. Science reads that. Well, Lemaitre published it in French in 1927 in this obscure journal called the Annals of the Scientific Society of Brussels. So then he published it he translated it and republished it in 1931 in the Royal Astronomical Society journal, which is a widely read journal. But now this is the "Thou shalt not covet thy neighbor's ass" department here. or the curious case of equation 24. If you look at Lemaitre's original article in the Annals of Scientific Society of Brussels, I speak enough French to fight my way out of a French restaurant. So I'll translate this for you. It says, employing the 42 nebulae presented in the lists of Hubble and Stromberg, and taking into account the proper speed of the sun in this direction, one finds a mean distance of this is 0.95 million parsecs, and a radial speed of 600 kilometers per second, such that it is expansion is, he doesn't say the expansion there, but the expansion is 625 kilometers at 10 to 6 parsecs. Thus we adopt this equation. Now this is Hubble's equation in here. Here's where he put it. Now, when Lemaitre had translated his article in 1931, equation 24, occasion 24, he just puts, from a discussion of available data we adopt, he X'd out Hubble.
Of course.
He got rid of him.
Because he did it first.
Well, as Henry Kissinger said, academic politics are so vicious precisely because the stakes are so small.
Yeah. Academics.
You would know, huh?
I should.
So now let's talk about. So now let's talk about astronomy and cosmology. Astronomy is the study of the heavenly. There's a little overlap here, but astronomy is the study of the heavenly bodies. Cosmology is the study of the universe. They're two different subjects with some overlap.
Of course, they're two different. One is Marilyn Monroe, and the other one's.
I was going to say one is lipstick and makeup and eyeshadow.
Heavenly bodies.
And right there you go. Now we've been looking at the maps. This was made when Dick was a kid. This was
oh, thank you.
1479 BC, 1548. Senamjut the Great, who we all remember.
You weren't a kid; you were a teenager then.
Right. He's going into high school.
Jeez, you got.
So they were mapping the stars then, and they were mapping them accurately. This is very important. They were fascinated by them, and they worked nights, and they were mapping the stars. Now, there's two ways to project it, and this is the one that I don't know how many people have a telescope. I have a telescope, and you use the meridian projection to see where the stars are, and it's analogous to latitude and longitude, but the terminology is different. Here's the North Pole, celestial South Pole, and here's the right ascension is basically the equator. And now here, this is not right ascension. This is 0 hour right ascension, which is through Greenwich, England. Mm. And then every hour, so there's 24 hours in there. And it's also divided into 360 degrees. The declination is what you would call latitude, degrees up here. And this is just 360 degrees. And of course, the degrees are divided into 60 minutes into 60 seconds. That's what I'm most familiar with. And this is what you'll see when you say, look at this star, or there's this comet that's going, you set up based on your axis of your telescope is with the North Pole. So when you just turn these little knobs and as things move out of your range, you just move into them. There's also using Cartesian coordinates. I couldn't find one for the solar system or for the celestial system, so I just used a map. And this is not good for viewing, but it's much better for mathematics when you give something a Cartesian coordinate and there's a distance between them. And so you take the stars and make it, there's a Milky Way, make a Cartesian coordinate map of that. But this is what I'm most familiar with. Now, it gets a little bit more complicated because first of all, we have precession, we have nutation. Precession, which we've all seen, the slow movement of the axis of a spinning body around another axis. So you got your gyroscope, you spin it, and then it starts, its axis goes like that. We have precession. So then this guy says, so you mean the celestial coordinates aren't really the celestial coordinates? There you go. And so what we're in is what are called from the International Astronomical Unit, we're in, and epochs have been made every 50 years. They remap or relocate this. Make the correction for the celestial sphere. Everybody knows the Earth is the center of the universe, and the celestial sphere is around it. And so the celestial sphere is rotating. The Earth is still. Really? So we're in epoch 2000. It's also called J2000.1. But they're talking now, because of these satellites that are giving us data, they're talking us now of not going out 50 years, but making a shorter epoch. So everyone will know what epoch they're in. It's easy to know because they'll say 2025 or 2030. Or you could just do it by computer software, but then everybody, including amateurs, have to have the software. So they probably don't want to do that. They probably will come out with another epoch. So here's precession. Now, the Earth is round, and it's always been that way. Aristotle noted that in 350 BC, during a lunar eclipse, he saw the shadow of the Earth was round. They knew the Earth was round. The business of Earth being flat was a canard. And Eratosthenes, he is a Greek in 200, around 200 BC or so. He measured the length of shadows at noon in two different locations: Alexandria, Virginia, Alexandria, Egypt. Alexandria, Virginia is good enough. Close enough for government work. Alexandria, Egypt, and then at the Aswan Dam, which is called Syene. Now, this is just about at the equator. So in the summer solstice, the sun was virtually directly overhead in Syene at an angle in Alexandria. And he calculated the Earth's circumference to be 24,662 miles. He used the stadian, which is the Greek measurement in feet and inches. But so it's the actual circumference 24,901. So he was off by 239 miles. That's pretty good for a couple hundred years BC. Pretty good. They could do math then. And then now Hipparchus on 127 first noted precession. And what he did, he made careful measurements of the position of the stars and their changes from old Egyptian star maps, which were very accurate. And he observed that the stars were shifting over time. And he compared the star positions during equinoxes and solar eclipses, because he knew exactly where things were in relation to other years, other decades, centuries. And he recognized there was a slow wobble in the Earth's axis. He figured out that precession was greater than 1 degree per century. So a full precession is 22,000 years. Then we have nutation, which is the periodic variation angle of the Earth's rotational axis from gravitational effects of the sun and the moon. And this cycles every 18.6 years. So the celestial poles shift slightly, and that affects astronomical observations, locations, and coordinate systems. So the period creates periodic variations in the position of the equinoxes along the ecliptic plane there. So now you have precession and nutation, which changes things. And when you're starting to get a lot of data and you're trying to make sense of it, you gotta take all these things into account. Now, the people have been noting the changes in position continuously since forever. And the table is called ephemerides. Positions are ephemeral. And now their software algorithms will correct the coordinates, XY coordinates over time. This is 1252 AD, Alfonso X, King of Spain. This is his court's correction for the stars. Now we're going to switch over to a little cosmology. So we need units of measure. Then you want to take a physics course, the first thing they do is torture you with units of measure. They do. So you got to go through it. Then everybody knows the astronomical unit, the distance of Earth to the sun, the average distance. The light year, everybody knows what that is. And the parsec, which we'll go over, it's 3.2 light years, 6 light years, based on the parallax method, which we'll go over. So a megaparsec, which is really the measurement in cosmology, is 1 million parsecs, which is 3.2 million light years. That's really our rule. That's how we're going to get there. So if we look at the parsec, which stands for parallel arc seconds, a degree is 360 minutes, the 60th of the degree, and the arc second is 1/3600th of a degree. So what you do, you know where the Earth is in the sun, and you find a star up here, and what that star moves, here's the view in the summer, here's our very distant stars, which have no real parallax, here and here. And the closest, you find a star that moves like this, and it subtends 1 arc second. Now, if this subtends 1 arc second, you know this distance here, you know this angle here, you know this angle here, and this is a right angle. So with a little trigonometry, you can figure out the distance to the star. And that's, by definition, 1 parallel arc second. There you got it. Now, that you can only find these arcs out to about 32,000 light years to actually measure, because then you can't find enough. Can't measure. These just don't seem to move. Now, the Milky Way, sort of put your bearings. Milky Way is about 100,000 light years across. So you can measure parsec, use this method of triangulation for about 1/3 of the diameter of the Milky Way. And that's as far as you can determine distance with parsecs. But it does give us the megaparsec ruler, which is really the important point. This is just how we got there. Now we're going to do look at a little wave shift in the z scale, which a little bit later we'll do some math and show you how we get there. But the z scale is a scale that gives us the stretching factor, the expansion shift. The z is the cosmological redshift, the expansion of space. Space is expanding all the time. It's hard to understand how it can do that, but it is.
What is expanding into?
Nothing. There is nothing there. That's what we're going to talk about. That is the mystery.
Because it can.
Right.
That's why Euclid is up there.
There's a little bit of a problem here, which I won't go into, but when they look at the Higgs boson and the energy in the vacuum void and how fast we should be expanding, it's off by 28 decimal points, 28, a factor of 28. And we should be flying, by calculation, we should be all flying apart at more than the speed of light. And that's probably not happening. So let's go back to how we get there. Hubble's law.
But it probably is, but it's relative. So everybody's flying apart at the same rate so that we don't see any motion.
Right, there you go. Hubble's law. But Hubble thought this was a constant. This is Hubble's constant times the distance gives us the velocity. So Hubble's constant is the rate of expansion of space, originally thought to be a true constant by the data he could collect. But in fact, expansion is becoming greater over time. So to look at it sort of in a graphical sense, here's time zero where we are now. If we look at it when the universe first started to expand, it expanded very quickly. It's not clear that it's a ballistic event, but it expanded very quickly. And then it began to slow down, and then began to speed up again, is the universe now. And the theoreticians say that the expansion rate will increase in time due to dark energy. We'll see about that. So here are our measurement standards. We got our parallax, we know that. Then red giants, pulsating stars, which will go over the Cepheid variables, Mira variables. The most important one, the type 1a supernovae, quasars, and then sometimes they tie things one brightness to another known brightness. So the Cepheid variables. Now, Cepheid variables really don't do anything different than other stars do, but they just do it rhythmically. They pulsate and change over time. You can see they get brighter and darker, brighter and darker, brighter and darker. What happens is that helium has a nucleus, which is 2 protons, 2 neutrons, also called an alpha particle, and 2 electrons. And when it's pulled by gravity to the surface of the star, and then it gets to be double ionized. And when it's double ionized, it's opaque. The heat builds up because the light is not getting out. Photons are all blasting around. And then kaboom, they're suddenly expelled out there, and the brightness, and then they can congeal back. The electrons can join back into the alpha particles, and light gets out, and it gets brighter. Then, and as it gets out, it gets cooler, and then it is not near all the heat of the star. Then it sinks back in, then heats up again, gets double ionized, and blasts out again. And so these go up and down and up and down. There's a good variation, but they're 500 to 300,000 times brighter than the sun, but they are half the mass of the sun. Well, only stars with half mass can do it cycling, but all stars do this. The distance of the star is determined by comparing its known luminosity to its observed brightness. So that's one standard candle. The myriads do the same thing. Now, this is the most important and interesting candle, supernova. This occurs in binary systems, 2 stars orbiting one another. One of the stars is a white dwarf. which is an old star. We know and all the helium and hydrogen also has been used up. Now oxygen and carbon dioxide. And it's limited to 1.4 solar masses. And if it gets any more masses, like from its partner, it gets more gravity. And that will reach the fusion pressure of the carbon. And then the carbon starts to fuse, and kaboom, this thing explodes. And you get a supernova. And because it explodes just after it exceeds 1.4 solar masses, it's very uniform in its explosion. So it's a very good candle to have because of the uniformity. And the supernova has a very consistent peak luminosity, so we know how far away they are. And then the quasars, which are quasi-stellar radio sources, in these things, as matter is pulled into a black hole, you get a lot of heat and radiation, and then that's projected out into space. It's not in the black hole yet. And they emit a very broad light spectrum, which is important, it's very broad. And the luminosity can be estimated by the width and intensity of those lines. So the quasars are very useful too. So now, I'm going to blast over to the weird concepts of singularity.
Oh, these weren't weird yet?
No, beginnings, we haven't got to the weird.
They were pretty weird.
No. Now, you have to remember, this is a model. This is not, nobody observed this. There was only one guy around at the time. Okay, so nobody else observed the singularity.
May have been only one guy around at the time.
As best we know. It was said to be a point of, this is one model, there are other models, a point of infinite density and of infinitesimal volume containing, now here's the mystery, all matter, energy, space, and time. There was nothing around it. There was no void around it. It is everything.
So it's been documented. It says in the beginning, and that's describing this.
Bereshis, in the beginning.
In the beginning, kind of it's just a very general term.
Well, that's a scientific term. It's documented. You know, everybody has a document. It says in the beginning, and that's this point.
Wait, but that says there's time. If there's a beginning.
Yeah.
The beginning of time.
There's no time.
But
time is in there. Time is in the singularity.
Right. The beginning has time implied in it.
Absolutely. And the important point is that if it's a small uniform point, its uniformity means everything, all the energy is going to be the same throughout this very tiny point. Because it's so small.
It presumes an end as well in the beginning.
Well, there always is an end.
The big guy knows.
Well, we're working on it. We're working on that.
Yeah, I don't believe that.
Now, this is hard.
We hope it's not in our lifetime, but we can go forward.
This is hard to understand.
That is your lifetime. Yeah.
The singularity of the universe implies that there's nothing around the singularity. Nothing. It's not a point in space. There's nothing there. It contains all matter, energy, space, and time. And the reason that now, and always in science, in every science we all had, you have a model, you get data, you tweak the model, you have a new model, you get data, you tweak the model, you tweak the model. That always goes on. But you start with a model. And this is and if you start with the singularity, a lot of the stuff works after that, works into that model. It's consistent. It doesn't mean it's true. It means it's consistent. So now, the quote Big Bang. Now, when the scientists can't explain something, they say, oh, quantum fluctuations, like they know what that means. And so why did the singularity change at all? No, quantum fluctuations, like, oh, sure. Made the original singularity unstable and began to expand. It's not clear there's an explosion per se, a rapid expansion, if there's a difference. And our current expansion extrapolated back would take almost an infinite amount of time to revert to a singularity. So the original expansion was very dramatic. So it's much like a person at our expansion rate, walking halfway to a destination, halfway and halfway. You'll never get there. So the model has to have early expansion, very, very great early expansion. So now in the early expansion, by calculations, the light, the photons, it was almost all photons, very little matter. Matter, but a lot more photons, was in the visible range. That's where it was. A vast amount of energy, and the early matter was in its smallest form that we know of, which are quarks, protons, and neutrons. And as the universe expanded, these high energy photons gradually contained less energy per unit volume, so they redshifted. And just by way of review, here's a spectrum. So here's where we can see right over here after the red would be near infrared, which we can't see. And then infrared, then the longer microwaves and the very long radio waves. And on the other side is the ultraviolet X-rays. And if we went over here, we'd see gamma rays and the very high gamma rays and very high cosmic rays. Now maybe we all used angstroms in the old days, which is 10 to the minus 8 centimeters. Didn't we all use angstroms? Yeah. So, but
quantum all the time.
Yeah.
I used to use it, but then the police got involved in the story.
So with the expansion of space, high energy photons, space expands and the speed of light remains constant, wavelength becomes longer, which we'll show you more of. Now, cosmic expansion, the stretching of the light wave, is in it. They say, well, why does that really happen? And they say, oh, it's an intrinsic property of the expansion of space, which explains nothing. But light always travels at the same speed, so the wavelength increases. So if we look at the cosmic, now this is different than Doppler redshift. The Doppler shift occurs right away. If you're running away from me and say hello, that wave is already stretched from as soon as it leaves your vocal cords, it's already stretched. And it doesn't stretch anymore along the pathway. With cosmic expansion, the wavelength is expanding all the time as the cosmos expands. So you start with a light wave here. You can see with each frequency wave, it gets a little bit longer. So cosmic light from a closer galaxy, a couple billion light years away, reaching us at the same time as more distant light at the same time, will not have experienced as much expansion of space. So it won't be redshifted as long.
Can I ask you a question now, Jerry?
Yeah.
Why do we know, we have this concept of expansion and redshift. When and how was that proven to be what's going on? That the light that originated, looking at your picture, in the blue range, ultimately morphed into the red range.
Are you saying why isn't it just losing energy?
Well, how do we know that the wave has a property of being a sinusoidal thing, however you want to do it. How do we know that the period keeps changing in that wave?
The color is the wavelength.
I know, but
and the farther away, the longer the wavelength. You have a candle. Because the supernova is at a given distance. You know what it is.
Because we're making an assumption that the wave changes, but
it becomes longer.
Right. But why does it become longer? What's causing it to change?
You just drilled right into this slide. They say it's an intrinsic property of space. Like gravity is an intrinsic property of matter. There's no explanation. Can't find an explanation.
Okay.
It's a property of space to do that.
Okay.
Very unsatisfying.
Okay.
So it's like the Doppler shift. It's like it.
Well, the Doppler shift occurs right away.
It's analogous to Doppler.
It's analogous, but Doppler is right away.
The farther away things are, the longer the wavelength becomes.
Right, but it's progressively longer.
Yes, Doppler shift
Doppler shift is because you're running away from me.
Well,
here, the space is expanding.
Can't you make to Dick's point? Can't you take the same analogy that it's making this red shift, and you think all of a sudden it changes after a certain, that isn't happening right away. Maybe it is happening right away, but we just can't measure the change initially, and finally the shift becomes large enough that we can measure it, and then that's what we see as a red shift.
That is what happened. They did do the measurements because that's how they proved the Hubble's constant is not constant, because they made more measurements. Hubble made his. That's where they came up with this.
Now, Dick just presaged this graphic here. Here, you got it. I mean, no, you got to think about this stuff. This thinking. Hubble assumed the rate of expansion was linear. Now, he only had the equipment that he had, okay? And he could only see out to a little less probably than 1 billion years. Yeah, this is a million parsecs. Now, this is a graph of his data. 6.5 million light years, but he could almost get to 1 billion. So now this is the best fit data. This is not like he measured it precisely. This is a best fit. And he had a limited number, as we saw in the articles, he had a limited number of galaxies that he looked at, but he thought it was linear. And this is what, and that's the best he could do in 29. So if we look at the Hubble constant and look at the light wave, he showed it was enlarging over time by measuring progressive redshift as distance increases. So if you have a wavelength here that goes this certain distance here, double a certain distance, to double the distance, the wavelength is twice. If it goes 4 times the distance, the wavelength has to go through all 4 blocks. And that applies to every distance that he could measure. So he thought it was linear throughout, because that was the data he had. Okay, now, so I want to talk about the Z shift. So I have to do a little bit of arithmetic. I think I have to get myself a pen here. Okay. Now, I thought I would make this so that it could be understood by bankers. Have a pen here? No, let me get a pen. Oops. Come back. Now, if you were to go to the bank and you were to borrow $1, I didn't mean to call it, and a year later you paid them $1.05. Well, what's the interest rate? Well, you just know it's 5% without even thinking. You just say, oh, it's 5%. This is Z. This is the expansion rate. But how did you actually figure this out? Well, what you did was you took the final expansion minus the initial, the final amount of money minus the initial amount of money divided by the initial amount of money. This works with any loan, whether it's $1 or $50. $50 always matters the same. So it comes out to be 0.5 over 1, or 5%. That's how it works. So if we can do the same thing with light waves. So we look at the lambda is the light wave. We look at the observed, that's what you see here. Observed minus the emitted, observed is here, minus the emitted, the initial loan, the light that was emitted, divided by light emitted, and that equals a number called an expansion rate, which is the percentage, which is Z. So why do we do that? Because then, let me multiply this out. I'm going to move this over here to the other side. So lambda observed minus emitted equals Z times emitted. So what? So then I can move this over to the other side and I get Z times emitted plus, goes to the other side, lambda emitted. And then I can factor this, so we get something meaningful. Z plus 1 lambda emitted. Now I can take this and move it down here. Now I get something that's useful. Then just take the observed, what came to the Earth, over the emitted, which is from my standard candle, which I simply know what it is, and I get that equal to Z plus, what happened there? How did I erase the whole thing? How did that happen?
I'm seeing the whole screen blink on and off. It stopped doing that about just as I started talking.
Is it black?
It's now stable, and I can see I can see a screen that just says Z shift on it, and now I can see your writing.
Okay, well let me just the last equation. I'm sorry I erased it. I don't know what it is.
Scribble.
Lambda observed, maybe. Lambda observed over lambda emitted equals Z plus 1. So now the point is I only have 2 things to work with, observed and emitted, which is what I got. So then the Z plus 1 will be the, Z plus 1 will be the amount, of the ratio of these 2. it says how much it expanded. So that the Z will be one less than that. So if the Z were 2, then the expansion would be 3. And so the language that they use is the Z. But if you want to know the expansion, if I tell you the Z is 4, expansion expanded 5 times. But now we just look at redshift. And now we just look at emitted and observed. So here's a graphic. Here's the age of the universe, and here's the redshift Z.
So, all right, so how do you know what the emitted is?
Because it's a standard candle. It's the type 1A supernova, and you know what that is.
Okay, so that number, 17, that number exists, and everybody has it in their back pocket, and they just use it.
However, to expand on your point, there's a redshift that came in. So they have to take that redshift, calculate it back to the real frequency that was emitted, which they know they know what frequency was emitted from a supernova. So you take that redshift and you calculate it back to get the real color that was emitted, the real frequency that was emitted. So there's a little bit of a calculation. You don't just look at the light. And the brightness has to do with 2 factors. It has to do with the frequency, like the high energy cosmic waves have a very high frequency, high energy, and the number of photons that hit you. So you get the brightness because you know the frequency, and then all you do is you take your photometer and you measure how many photons hit you, and then you know the brightness. So if we look at the age of the universe over here, complicated stuff, age of the universe here, and the redshift here. So if the redshift is 4, that means the universe expanded 5, the space expanded 5 times. But this is the language that they use. This language that you'll hear. So here, with the redshift is 2, the age of the universe is a little less than 4 billion years, gig years. And if it's up at 6, it's 1.5 billion years or so, whatever that is. And so you look at the redshift and you can tell that how far back in the universe you were looking. I want to get rid of this pen. And this shows things that the Hubble, new cursor. No, the Hubble saw lots of galaxies out here. As it looks out farther, billions of years, as space expanded, they're farther apart. You get fewer of them. I was a lad. When I took science, the observable universe was defined as celestial bodies whose light had reached the Earth. Observable. Now, what was left unsaid was, well, we can't observe them all because our telescope's not big enough. But you get a bigger telescope to observe. Nowadays, they also include dark matter, which is not really observable, but its effects can be seen. So it can be derived what it is. So that's the observable universe now includes the dark matter as well as the celestial.
Or conversely, observable limits you to visible light.
Yeah, but it's not really observable. Nowadays, they include dark matter with that. Not when I was a lad, though, because we didn't have dark matter then. No. Didn't exist then.
Just it doesn't matter.
Yeah, it doesn't matter.
It did exist, you just didn't know it.
So here's the Mount Wilson. That's where Hubble was, in Pasadena. So he had a 100-inch telescope, which was the largest in the world. He was a mile up to get rid of the twinkle from the atmosphere, and he could see out just about 2 billion light years. You saw his graphics. Whatever it was.
That's bigger than the one in Chile, or where?
Chile wasn't there then.
Oh, Chile wasn't there then?
Not at that time.
Oh, not at that time. Okay.
Oh, so then we got new tools all along Palomar and Hawaii, whatever that was called. It's
two of them up there.
Yeah. And so now the Hubble, they do visible light, gets out to 13 billion light years. That's a long way. The James Webb only goes a little bit farther, 13.5, but because they use infrared, which travels better through dust, they get better imaging. But a very narrow field. It's not a map. It's just looking at stuff, looking at astronomy way out. Now our cosmology we get to with the Euclid, which is doing wide field surveys for large scale structure. So in the visible infrared, which we've gone over, out to 10 billion light years. So it doesn't go as far, but it's going to map a third of the sky, more than a third of the sky. And of course, in 97, the supernova, this one found to be dimmer than expected, indicating the universe's expansion was accelerating. And that's what we're going to be looking at. Now, a point measured at the a meeting here, I think Bob Primack brought this up. Could galaxy light redshift be due to a loss of energy as photons travel over vast distance of space? I.e., it's not a cosmic expansion effect. It's just, well, it's a good question. So you got to look for other evidence. Now, one thing that doesn't exactly explain it, but it's a piece of evidence. Here's early in the universe, early in the singularity. This is not drawn quite right. I clipped it, but then I realized it wasn't drawn quite right. Photons got entangled with electrons, and they couldn't really escape very well from the singularity. After about 380,000 years in the early expansion of the universe, it cooled enough out there so that the electrons could combine with the hydrogen, and then the photons could begin to escape. And they also, as space expanded, they became longer into the microwave range. And what we see is in the universe, a big place, and the microwaves are coming at us from everywhere, these old microwaves. In the singularity phase of very early expansion, photons are in close proximity and the energy equilibrated. So if space expanded uniformly, they cooled, lost energy per unit volume, uniformly. So we see great uniformity in the microwave length throughout the universe. You see 380,000 years, you had what they call a recombination, but it's really a combination. When the hydrogen could join with the electrons, there's about 3,000 degrees Kelvin. Photons were in the visible range at the beginning and could escape. As it expanded, it cooled to 2.726 degrees Kelvin, plus or minus 0.001. Now, if there had been temperature non-uniformity, you'd have different wavelengths out here. And these couldn't equilibrate over time now because they're too far apart. These are billions and billions of light years apart. So the stability of the cosmic wave background suggests that everything began at a single point, but it doesn't really answer the question about whether it could decline over time, but it seems unlikely. So what we're going to look at is baryonic, meaning ordinary mass, acoustic oscillations, which I'm sure you're all familiar with. You ever hear of them?
I haven't heard of them, but I think I know what you're talking about.
Okay. Well, baryonic particles, of course, are masses. We know them. Now, there's no stars here in this diagram. This is just quarks forming nucleons, protons, electrons, joining with electrons to form hydrogen and helium. And these are all through the universe. And they begin to condense by gravity. And initially, as this condenses, heat comes up because they're all going in different directions, coming to the center. And then at some point, the heat literally boils over and blasts out a mass of hydrogen out to here. And as it gets to a certain point, it cools and loses its momentum and begins to congeal and to form stable stars. And then the stars congeal to form galaxies. And so this is a baryonic acoustic wave, which provides a physical, not a light wave based, physical record of the expansion of space. Now, this is drawn as stars, but originally it was just hydrogen. So regions of higher mass density condensed by gravity, heat and photons blasted out the early matter till it cooled and then condensed out here. It's really a sphere, although it's drawn as a circle. The expanding sphere of protons, quarks, nucleons, electrons cool. And then these acoustical waves expand. Now, these acoustical waves, which then congeal into stars and galaxies with a very dense central galaxies, expand with an enlargement of space, like a donut rising. So as we look back in time, they should be smaller in diameter. And this provides the physical record of the expansion of space. So a second unrelated piece of evidence. So we look at the baryonic acoustic oscillations. Here you start with just matter condensing. It's drawn here as stars, but you have a baryonic acoustic wave, and then as space expands, they get larger and larger. So that you go back in time, they should be smaller. So as you look farther and farther out in space, it should be smaller.
Where does the term acoustic come from? Is that to make it analogous?
It's just
analogous to what we think.
Yeah, you can't hear them.
So
It's just
like a sound wave.
Yeah, it's just an analogy. So can we directly review the mass forming baryonic acoustic waves? Nope. Too much overlap. Can't see them. So what you do is you find a very dense cluster of galaxies here. And then you look at the likelihood of finding galaxies as you go farther and farther out. It gets less and less and less. And then suddenly there's a whole ring of galaxies and you find them here. So the number of galaxies goes out more. And so this corresponds to the original sphere, which condensed to form many galaxies. Now, to do all this, you need tons and tons and tons of data. You have to see billions of galaxies to do this. And this is what the Euclid can do. It can get billions and billions. So, in summary, the frozen baryonic rings is represented by the statistical analysis of galaxy distances have expanded over time, consistent with the expansion of space. Now, here we go. No such thing as settled science. I think that Ted brought this up in another context. The estimates of how fast the universe is expanding don't line up. There is uniform agreement that everything we measure is accurate. Our measurements are not inaccurate. We measure frequency well. We're good at that. We are good at measuring frequency. And light. So the cosmic microwave background suggests a Hubble constant of 68 kilometers per second per megaparsec. Baryonic acoustic oscillations are over here. Cepheids are over here. Red giants here. Mirrors here. Quasars, red masters. And you see there are places where there's no overlap. This doesn't. Red giants and Cepheid data don't even overlap. We can say, oh, it's just the margin of error. These don't only overlap with red giants. So now, in a recent meeting of the International Astronomical Union, this is when they have data that doesn't agree. It's called a tension. The tension is there, and they said, well, is this a tension or is this so serious that it's a crisis? And I'm thinking, wait a minute. A crisis is you get up in the morning, you take a shower, and then you go down to the kitchen, and the shower is right over the kitchen. You look at the ceiling, and it's all wet, and the water's dropping down. That's a crisis. This is not a crisis. So cooler heads prevailed, and it remained a tension. But I thought that was so. So the Euclid is going to do cosmology. It's going to mention the expansion of the universe, galaxy clustering, and provide more information about expansion. Look at the distance size of the baryonic acoustic oscillations, which should be smaller. And the large volume of space will provide more statistical certainty. And they're going to start looking at all the other methods. And the mapping large scale is just to make a 3D map, the large scale of the universe with the dark matter and the theory of dark energy, and determine the distribution of dark matter. Now that's in contrast to James Webb, which is astronomy, studying the universe in infrared, creates beautiful pictures of galaxies, stars, exoplanets, and using deep field imaging spectroscopy for all these detailed structures here. Now, Euclid, they got out of position. They're in position around the fall. They were launched in July and in the fall. So they start taking some pictures. I think this is mostly PR, but they just sent out some images, and then they sent out some more images in spring 2024. Now, I've seen two different statements of when the first data dump will be. First statement was early 2025. Both, I don't know when they're dated, but early 2025 or maybe late 2025, but I don't know when the first data dump will be given. And then the second data dump will be 2026. It will all be published. Now, unlike the Euclid and like our friend Scott Kenyon, he had time on the Hubble. Unlike the JWST and the Hubble, where you applied as a scientist for time to image this or to image that, and you got your time if you qualified. There's no timeshare. Scientists in the Euclid is just going to do its mapping, and that's it.
So it's all been preordained before.
Yes.
Before.
Mm-hmm. Yep. Now, here's the deal.
It's been preordained.
What's going to be looked at?
What Euclid does.
What Euclid's going to be done. There's no good ideas. Send us your idea. We'll give you an hour.
All right. So Jerry, so with Euclid, you're saying it's mapping about a third of the universe.
Yes.
You know, in
visible
universe.
No, I'm sorry. Of the celestial sphere.
Celestial sphere, 1/3. So after 3 mappings, right? It maps 1/3. Can it?
No, it's just going ka-ching, 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 ka-ching,
Okay.
like that. So it's map what it can see.
All right. So at some point in time, it's going to finish mapping that third.
Yes.
how long will that take? Did they estimate?
Just a few years.
A few years.
Yes.
What happens?
I think maximum is 5.
Okay.
Max 5.
All right, maximum 5. So say it is 5 years.
Yeah.
What happens year 6?
There may be another mission for it, but they haven't decided. That's what they're saying publicly. So I think what they're really saying is, well, that's a very good point. I didn't think of that. Good point. Turns out they get. But here's the problem with that. What if the data isn't consistent with the past year, with the current model?
And you make other measurements.
What if, for example, here's a shows a nice.
And you adjust the data to make sure it fits.
Right. Adjust the data.
Broken.
It's supposed to fit this nice smooth acceleration. What if it doesn't? What if the redshift show they're increasing and decreasing and increasing and decreasing? What if the baryonic acoustic oscillations show the same thing, but they're not in sync? Well, for one thing, all those professors are going to lose their of cosmology are going to lose tenure. That's for sure. That's for sure. That we know. There'll be other professorships galore given out on the new analysis. Yeah. So the sum total will be about the same. It's like a constant. There's a constant there. That's a question of what they're going to find and how it's going to be. Okay, so we're ready for the data. Bring it on. That's the end.
Well, good question. The answer why all these measurements are not aligning, is that where dark energy comes in?
No. No.
To make that.
Well, they should. Dark energy. Let's just do a little dark energy stuff. The weirdness, I made this slide, the weirdness of dark energy. Now, as space expands, dark energy must increase. Because if it were just the same, they call it an energy budget. That's the term they use. So they say the singularity had an energy budget. This is a problem. That hasn't been answered. If the singularity had an energy budget, meaning a certain amount of energy, if some of that is in dark energy, or most of it's in dark energy, as space expands, the amount of dark energy per unit volume has to decrease. Conservation of energy. So what they're saying is, oh no, it's not decreasing because it could be the other way. It's a property of space. Well, that's the ultimate free lunch. Maybe the universe is the ultimate free lunch. Mm-hmm. What happens to the law of conservation of energy? Mm-hmm. And they say, oh, well, that applies to regular physics, but not in relativity. Wait a minute, a law is a law. Nobody's above the law except when they are. Well, is it? If you haven't started with an energy budget, that's the weirdness of dark energy, and that's a model. There's nobody's bottled and sold dark energy. It's a model. They try to explain this.
There's a simple solution. You go back to bloodletting.
Right. Explain it. But then when they talk about, as I mentioned, the Higgs boson and the amount of energy that's in the vacuum void, it's 10 to the 28 times greater, and we should be. It doesn't match up. It doesn't match up. And
just to be clear, though, conservation of energy is a thing you were taught in high school. You have to define what energy is, and energy is the thing that is conserved when you have time independence. So you then go to Noether's theorem, which tells you that every conservation law is tied to a fundamental symmetry. So as long as if the universe is infinitely long and it doesn't matter when you do an experiment, you expect to find conservation of energy. But the explanation given as to why dark energy seems to violate conservation of energy is that the universe does care what time it is. The universe at the beginning of its existence is different than the universe now. And if you don't have time symmetry, time translation symmetry, you can't expect to have conservation of energy. So it's important to understand that it isn't just like, oh, let's just throw it away because it doesn't seem to work. It's conservation of energy comes from a fundamental symmetry.
So somebody wants
that symmetry isn't there, then the conservation.
Well, yeah.
So Adam, to put it in different terms, the rule Say it again, Mike.
I said that statement reasons back from what's being observed.
Yes.
Right.
In other
We're always
words,
building models.
you're not observing the result from the conservation of energy, and therefore it's not conserved.
Well, but where does
Or I was thinking you could put it differently, Adam. It is that the rules about conservation of energy are complete. There is another part of the equation called time, which we are assuming to be equal to zero or have no effect, but in fact is non-zero, that does have an effect, 0 or 1, depending what
sort of. I'd say,
and it's something that we don't know about. So it's an error factor, if you will, so that it does apply if you want to make sure it works over all instances. Is that a fair statement?
sort of. I think it's not like it's an error. So conservation of energy isn't. It's not fun. It's not a thing that there's a tablet that says conservation. Energy is conserved. It's a thing that we've observed when we do experiments in the lab. You usually find that energy seems to be conserved, right? On Earth, normal experiments, you see energy is conserved. Does that mean it's a universal law or not? It is in our everyday lives. But then, 100 plus years ago, Emmy Noether, one of the greatest under-recognized physicists ever, found this deep connection between conservation laws and fundamental symmetries of the universe. And the conservation of energy turns out to be linked to time symmetry, time translation symmetry in the universe, just like momentum, conservation of momentum is connected to translation symmetry in the universe. In theory, if I do an experiment over here and I do an experiment over there, it's the same experiment. And that is what actually drives conservation of momentum. And so if you turns out that your universe does care what time it is, then you can't expect conservation of energy to be a real thing.
Well, Einstein was
sort of like relativity. It's like adding speeds. If I'm going at 10 miles an hour and you're going at 20 miles an hour, we'll hit each other at 30 miles an hour. And that works really well every day when we're driving our cars and hitting each other. But it turns out that it stops working when we get up to higher speeds, which we found out 150 years ago.
Right. Somebody challenged Einstein about light travel always traveling at the same speed, and the guy said every time it could be different. You just change the rate at which time passes. And Einstein looked at him and said, "Exactly."
Right. But we're right. We have no idea what dark energy is. It is weird. We also have no idea what dark matter is. It may not even exist.
Well, there are other models.
Yeah.
Yeah.
Dark matter has a little bit more experimentation behind it, but still we don't know what it is.
What are the other models? Are there other models?
Nothing that really
Theoreticians come up with models all the time.
Yeah.
Lots of stuff is published every day. All these models that come out. There are models now about negative gravity.
Yeah.
Okay. To explain a lot of this stuff.
Yeah, that's what I read.
Negative gravity.
Yeah. So, to me, the biggest conundrum that I've come up with, where I keep thinking about this off and on, is the concept of time itself. And I can't wrap my head around it. Give you an example. General relativity says that as gravity increases, time decreases, which means to me that if gravity becomes infinite, which is at the center of a black hole, for example, time ceases to exist. It's zero. And that's what predicated my question to you about time at the beginning of the universe. What is it? We have models of time because we do measurements. And we think about time in reality because of the way we perceive reality. But I'm not sure what time really is.
Well, Dan Klebner, who was instrumental in the development of the atomic. Is he here?
Yeah, but I'm right.
Dan's here.
He may have forgotten, but we were in a meeting. He was talking about time, and afterwards, I asked him, "What is time?" And he said, "I don't know, but I can measure it to 9 decimal places."
Yeah, exactly.
Here,
Go ahead.
Dan, you want to tell us what time is?
Go ahead.
Not what time it is, but what time is.
The subject is very confusing to me, although not to many other people. But the fact is that time can't be talked about in the absence of matter. That time and gravitational fields are interlocked.
Mm-hmm.
The difficulty is that if you want to compare two clocks, you have to take into account matter around them. And in principle, that's all the matter in the universe. So this means you can't really write down a recipe for comparing two clocks, which is necessary when you define a physical standard. Now, if we don't know how to compare two clocks, it really means that time is an ambiguous quantity, in which case space is an ambiguous quantity because space is currently defined as the distance that light travels in a given interval of time.
Right.
So this worries some people, but not me. Never
Some people define time as what clocks measure.
But it's a very fundamental matter because time and space are the two fundamental metrics we use when we start building physics. Yep. So if they're on wobbly foundations, it means that everything is on a wobbly foundation.
That's right. And that's where the symmetries come in somewhat too.
So Dan, let me pose this to me a simple question, which probably is more complex. You said it's hard to create a recipe to compare two clocks.
Mm-hmm.
We have an experiment that's been ongoing for a long time now. We have a space station which is sitting out there at some distance from the Earth, that we all understand time travels differently for them than it does for us on the face of the Earth. And doesn't that give us data in order to create a recipe to calibrate two clocks and create that?
Well,
it may be a simple question, but I don't understand that.
Well, the GPS system is based on a systematic way to transform the local measurements of time made by satellites between different observers. And it's essential that you include that. You can consider it just a correction. I calculated once if you forgot that and we're trying to fly from San Francisco to the Newark airport, you'd end up somewhere near Washington, D.C. So that would clearly be a mistake. And that's a relativistic correction that is just built into the algorithm for comparing signals from two satellites. But we're not anywhere near the boundary where the comparison of clocks is posing a question. I mean, it's a remarkable story. Junyi at Jilla is sort of the emperor of this particular empire, and now they can compare clocks in the laboratory to about a part in 10 to the 18th, and he's working on pushing the the precision even higher than that. Nonetheless,
and that backs into an interesting.
pardon?
Go ahead. Please continue.
Oh, okay. So saying it's a very interesting subject. I don't really understand it. If most people don't seem to be concerned about it, so I think that's probably due to a superficial misunderstanding on my part. Nonetheless, it has me concerned now. That isn't too serious. I think physics is not going to be overthrown because I'm concerned, but I would like to understand it better. I wrote about this more than 10 years ago in the Physics Today, a little column called "Time Too Good to Be True." You can see where that comes from when you're at the limit where these problems of comparison become really significant. You're kind of at a point where the clocks are too good to be true. You don't know how to tell the time from them. So that I would love to get Johnny here to talk, but he's a wonderful person and he's much sought after. You know, when you get a Nobel Prize, there's always a burst of interest in what you've done, and the poor laureate is kind of tied up in knots for some time. I think with Johnny, this may be going on continually. Nonetheless, he is continuing to report higher precision in the comparison of clocks. So that's part of the history. The reason that I'm particularly interested in this, that I helped Norman Ramsey build the hydrogen maser, which at the time was about the most accurate clock. It's no longer the most accurate clock, but it has the advantage of being the most reliable clock. It makes a wonderful flyweight clock that most time standards laboratories now use in generating their output primary signals. So somehow I feel responsible for what's going on today because this is just one step in the series of many steps which have gotten to this incredible accuracy. So I don't know whether I've enlightened anyone about anything except my mental state.
Yeah. Still worthwhile. Yeah.
I'm getting there too.
Well, I think the pessimism comes from when you think about it, that eventually all the stars in the galaxies are going to be burned out, and all the available hydrogen for new stars is going to be used up. And ultimately, there will just be a bunch of dead stars expanding into a void. There'll be black holes, and that'll be it.
But aren't stars?
Well, my concern about that is the fundamental.
Eventually, you're going to run out of hydrogen. Did we lose Dan?
No, now we're back.
We're frozen.
Yeah, maybe.
Okay. The major question there is whether the universe is closed or open. If it's open and continues to expand forever, the conversation is over. On the other hand, if it's periodic and will collapse at some point back to its origin. We'll be having this discussion again sometime. So we have to
No,
be.
we won't.
Somebody else will.
We'll be too busy collapsing, Dan.
So the two models. That's right.
You know, there are about 200 billion stars or so in the Milky Way galaxy, and it's estimated, you know, visibly there are about 200 billion galaxies. So somewhere there has to be another planet. In the universe. Well, at least one. There has to be another planet with life on it other than this one. But I have good reason to believe that this is the only planet with chocolate.
Ooh,
And thank goodness we're here.
If assuming that there's life at some planet that's really far away, the chances of them being able to, one, discern that we have life, since all they can see is what we looked like millions of years ago, and two, unless somehow somebody figures out a way to go faster than the speed of light, they'd never be able to get here.
Well, that's true.
Not under the current model.
Correct.
Right.
Correct. So if there are wormholes or other science fiction-y
Right.
things that exist, maybe the whole thing changes.
It's 11:30. I just have one question for Dan. How would you grade Jerry's presentation today, Dan?
It always stirs me when I see beautiful pictures, and I saw a lot today. So, thumbs up.